this video, I will explain what is meant by reversible reactions and equilibrium and what is Le Chatelier principle. Reversible reactions. In some chemical reactions, the products of the reaction can react to produce the original reactant. These are called reversible reactions. To represent reversible reactions, you should use this symbol which have two arrows instead of the single arrow that represent the normal reactions. So, for example, when hydrogen gas reacts with iodine gas, that gives you a hydrogen iodide gas, and this is a reversible reaction as indicated by these two arrows. Equilibrium. When a reversible reaction occurs in a closed system, equilibrium is reached when the reactions occur exactly at the same rate for both the forward reaction and the reverse reaction. What do we mean by closed system? Closed system means there is nothing that gets into that reaction and nothing gets out of that reaction. So basically, the reaction is in a closed system. So for example, when we have a reaction between A and B as reactant, that gives you C and D as product. At the start of the reaction, the concentration of the reactants are high and they start to react at higher rate. So the rate of the forward reaction is quite high and the products start to form. As the reaction proceeds, the concentration of the reactants will decrease and the concentration of the products will increase. That means the reactants rate of the reaction between the reactants or the rate of the forward reaction will decrease and the rate of the reverse reaction will increase. That will continue until the rate of the forward reaction equals the rate of the reverse reaction. Then the system will be at equilibrium. At equilibrium, both reactions are still happening, but there is no change in the concentration of all the reactants and products. So there is no overall change. What is equilibrium? The equilibrium is reached when the rate of the forward reaction equals the rate of the reverse reaction and the concentrations of all reactants and products are not changed. So the concentration of reactants and products at equilibrium are not the same, but they are constant. The position of equilibrium can be either to the right or to the left. So if the position of the equilibrium is to the right, that means towards the product, so more of the products will be produced or the concentration of the products will be higher. And if the equilibrium lies to the left, that means more of the reactants will be there, so the concentration of the reactants will be higher. The position of equilibrium will depend on the following conditions. First, the temperature, and then the pressure in case of gases, and the concentration of reactants and products. This is called Le Chatelier principle. So what is Le Chatelier's principle? The principle states that if a system is at equilibrium and a change is made to any of the conditions, then the system will respond to counteract that change. Please note that this only applies to homogeneous equilibria, meaning that all the species have to be in the same physical state. So either all the reactants or products are gases or all of them are liquids. The equilibrium or Le Chatelier principles will not apply if you have mix of gases and liquids in the same reaction system. So what are the different factors that affect the position of the equilibrium according to Le Chatelier principle? First thing is the changing of the concentration. So if you have a reversible reaction like A plus B that gives you C and D, then if the concentration of one of the reactants or products is changed, the system is no longer at equilibrium. And then the concentrations of all the substances will change until equilibrium is reached again. So if we increase the concentration of one of the reactants like A or B, the system will respond by trying to decrease the concentration of the reactants and increasing the concentration of the product. So the reaction will favor the forward reaction, meaning the reaction now, the position of the equilibrium now will be more towards the right. And if one of the product's concentration is increased, the reaction will respond by decreasing the concentration of the products and increasing the concentration of the reactants. So the reaction will now, the equilibrium will now lie towards the left or towards the reverse reaction. The second factor that can affect the position of the equilibrium is the change of temperature. So if we look at a reaction like this one, where sulfur dioxide reacts with oxygen gases to give you sulfur trioxide, and the enthalpy change for the forward reaction is minus 197 kilojoule per mole, which means the forward reaction is exothermic. We know that for reversible reactions, if the one direction is exothermic, the opposite has to be endothermic. So the reverse reaction now is an endothermic reaction. We know that exothermic reaction will lead to an increase in temperature and endothermic reaction will lead to a decrease in temperature. So if the temperature is increased, the equilibrium will move in the direction to try to decrease the heat, so towards the endothermic reaction. And if the temperature is decreased, the equilibrium will move in the direction to try to produce more heat, so towards the exothermic reaction. The overall effect in this case for this particular reaction, we know that the forward reaction is exothermic. So if we increase the temperature, then the reaction will be shifted towards the left-hand side, toward the reverse reaction, towards the endothermic reaction. So the yield will decrease or the concentration of the products will decrease. And if we decrease the temperature, then the reaction will be shifted towards the right hand side or towards the product, so there will be higher yield if we decrease the temperature in this case. The third factor is the effect of pressure change on equilibrium. Again, let's have a look at this reaction between sulfur dioxide and oxygen to give you sulfur trioxide. You can see that the number of moles on the left-hand side for the reactants is in total is 3 moles, while the number of moles for the product side, the right-hand side, is only 2 moles. And we know that increase in pressure means that the same number of particles will occupy a smaller space. So, according to Le Chatelier principle, the system will respond by trying to counteract the change that has happened. So, if we increase the pressure, then the system will be shifted towards the side that has a lower number of particles, because then it wants to decrease the pressure. Decrease the pressure meaning reduce the number of particles that occupies that particular space. So if we increase the pressure, then the reaction will be favored to the side which gives you the lower number of moles or lower number of particles. In this case, if we increase the pressure, the reaction will go toward the forward reaction because there are 2 moles of the products. And if we decrease the pressure, then the reaction will be favored towards the side that has a larger number of particles, trying to increase the pressure back again to reach the equilibrium or to regain the equilibrium of the system. So if we decrease the pressure, then the system will go towards the reactants. So overall for this one, if you increase the pressure, you're going to have more of the products, so you're going to have higher yield. And if you decrease the pressure, then you're going to have more of the reactants, so less product and then lower yield. The use of the catalyst and the position of equilibrium. When you use a catalyst, the catalyst will increase the rate of both the forward and reverse reaction at the exact same rate, which means that it will not affect the concentration of the reactants or the products. It will just help to reach the equilibrium faster. So the use of the catalyst does not affect the position of the equilibrium, does not affect the yield, but it only helps to reach the equilibrium faster. That means that the use of the catalyst is very useful because then we're going to have a faster reaction rather than having to wait for a long time until we reach the equilibrium. In industry, the reaction conditions chosen are a compromise. So, for example, if we look at the industrial production of ethanol by acid catalyzed hydration of ethene, the optimum conditions for this reaction is a pressure of 60 to 70 atmosphere, temperature of 300 degrees, and the use of phosphoric acid as a catalyst. When we look at this reaction, you can see that according to the enthalpy change of the forward reaction is exothermic. So let's have a look at the effect of temperature. This is the forward reaction is exothermic reaction. So when you decrease the temperature, the yield will increase because the equilibrium now will be shifted towards the ectothermic reaction, towards right, so higher product, so higher yield. But the rate of the reaction will decrease, meaning you will reach the equilibrium at a much slower rate because the temperature affects the rate of the reaction. But if you increase the temperature, you're going to decrease the yield because the reaction will be shifted toward the left, toward the endothermic reaction. So you're going to decrease the yield, but the rate of the reaction will increase, and also the overall cost because of the use of higher temperature. So to compromise, the optimum temperature here is 300 degrees, and this is going to be a compromise between reasonable yield and faster reaction. Then let's have a look at the pressure. You can see that there is only 1 mole of products and there are 2 moles on the left-hand side for the reactant. So if we increase the pressure, we will increase the yield because the position of the equilibrium will be shifted towards the right, toward formation of more of the product. We also know that increasing pressure will increase the rate of the reaction. So these two will increase the rate and the yield. However, what is the downside of using higher pressure? The downside will be the cost because you're going to need much tougher pipes to withstand the high pressure, and also because of the safety concerns with the use of high pressure. So to compromise, the optimum conditions will be 60 to 70 atmosphere for the pressure, and this is a compromise between reasonable yield and lower cost. And finally, the use of the catalyst. The catalyst will have no effect on the yield, as we can see, because the use of the catalyst will increase the rate of both the forward and reverse reaction at the exact same rate, so there is no effect on the yield. However, the rate of the reaction will be faster, meaning that we will reach the equilibrium faster. So the use of the catalyst will allow you to get the product at a faster pace. So instead of waiting for a long time, which saves a lot of time for the industry, and also it can allow you to do the reaction at lower temperature if your forward reaction is, especially if your forward reaction is an exothermic reaction. So if you use lower temperatures, then that means you can actually achieve good rate for the reaction and better yield with a lower cost.